everyone, I'm Ms. M. Kamali, Assistant Professor in the Department of Computer Applications at Jairaj Annapakyam College for Women, Autonomous Training. Welcome to our session on Computer Fundamentals. In this lecture, we will be learning about a very essential topic, binary arithmetic. In this concept, at the heart of all digital systems, including computers, calculators, and even mobile phones. So let's get started. In this module, we will explore what logic circuits are, how switching circuits works, Boolean algebra and operations, canonical form of Boolean functions, logic circuit implementation, arithmetic circuits such as adders, and finally, the physical devices, transistors, and integrating circuits that make all this possible. By the end of this video, you will understand how a simple Boolean equations becomes a real hardware circuits. Logical circuits are electronic circuits that perform logical operations on binary data, ones and zeros. They are the basic building blocks of digital systems such as CPUs, calculator, and microcontrollers. We classified them into two types. One is combinational circuits, where the output depends only the circuit input. Examples: adders, encoders, and multiplexers. Another one is sequential circuits, where the output depends on both current input and previous states. Examples: flip-flop, counters, and registers. Every computer system uses the combination of these two to perform logic and memory functions. Now, let's talk about switching circuits. Switching circuits can be in two states, on or off, which represent 1 and 0 respectively. They are used to represent logical values in hardware. Early computers used electromechanical relays as switches, slow but functional. They came vacuum tubes followed by transistors, which made circuits much smaller and faster. Today, integrated circuits (ICCs) contain millions or even millions of such switches on a tiny silicon chip. Switching circuits form the basis for all digital logic. To describe how logical circuits behave, we use Boolean algebra introduced by George Boole. It deals with binary values that take values 0 or 1. There are three basic operations: add, and output is 1 only if both inputs are 1, or output is 1 if input is 1, and the last one is not. Inverts the input. If A is equal to 1, then A not equal to 0. Let's look at quick examples. Operation AND, inputs 1 and 1, the output is 1. And operation OR, if inputs are 0 and 1, the output is 1. Last one is NOT operation. If the input is 1, then output is 0. These three operations from the foundation of all logical gates. A Boolean function maps binary inputs to a single binary output. For example, f a comma b equal to a plus b. So the given output 1 if either a or b is 1. And another example is f of a comma b equal to a divider c dot divider over line. So it's the set of b. The output is 1 if a is 1 and b is 0. Such functions describe the exact relationship between inputs and outputs in a logical circuit. In hardware, these relationships are implemented using logic gates. Boolean algebra follows a few postulates similar to ordinary algebra. Binary variables only 0 and 1. Define operators and or and not. Identity elements 0 for or, 1 for and. Descriptive laws. Commutative and associative properties. Using these laws, we can simplify complicated Boolean expressions into smaller, efficient forms. This is extremely helpful in circuit design. The principle of duality says every Boolean expression remains valid if we interchange and or and 0 interchange 1. Our example, so original value is a plus 0 equal to a, and the dual a c dot 1 equal to a. This property helps us derive new results directly from known ones. Some essential Boolean theorems include idempotent laws, a plus a equal to a dot a equal to a, null law, a plus 1 equal to 1, a dot 0 equal to 0, complement laws, a plus a naught equal to 1, a dot a naught equal to 0, involution, set of a naught equal to a, absorption, a plus a dot b equal to a, De Morgan's theorems, a dot b bar equal to a bar plus b bar, a plus b bar equal to a dot bar b dot bar. These theorems make circuit simplifications possible. In Boolean algebra, the order of evolution is important, not and or. Example, f is equal to a plus b c dot overline set of c. Here, first c is negated, then b and c is done, and finally or with a. This helps us interpret and design the right circuit. Boolean expressions can be represented graphically using Venn diagrams. Each circle represents a variable and shaded areas represent the true outcomes. A/B represents A and B. A slash B represents A or B. Venn diagrams are especially useful for visualizing set operations and logical relationship. That brings us to the end of this lecture on logical circuits. I hope you now have a clear understanding of how binary logic is represented and implemented inside a computer. In the next section, we will learn how to simplify Boolean expressions using kernel maps to optimize logic circuits even further. Thank you for watching. This is Ms. M. Kamali, Assistant Professor, Department of Computer Applications, Jairaj Annapogyam College for Women, Autonomous, Theni. Don't forget to like, share, and subscribe for more lessons on computer fundamentals. See you in the next class. Stay curious and keep learning.